Okay, thank you very much. Can you all hear me? Perfect. A little bit strange that I can talk very silently on this silent stage. Yeah, welcome everybody to my talk. My name is Christoph Hütt. I work at the University of Cologne in the Institute of Geography, and we are the working group for GIS and remote sensing. And as I'm a geographer, and I have a background in satellite remote sensing, multispectral and radar, and geographic information systems. I am problem driven, and I will not start with the methodology but with a problem and then introduce you the challenge and then how we solve this challenge using LiDAR and some parts also SLAM LiDAR. I'm happy to join Epotronic in 2026, and so I will leave the university. So if you have any research proposals, you have to be fast because then I will be at Epotronic. Well, the first project that I was given into with my satellite remote sensing background was green grass. And this project was about bringing cows back onto the pastures with innovative technologies like virtual fencing and remote sensing. So virtual fencing is a technology for cows. You put them a virtual collar on. They have GPS and they have cellular connection. And you can program virtual fences. And once the cow comes to that virtual fence, there's an acoustic and an electric stimulus that will prevent the cow to go over that fence. And here's some action. You can now think your paddocks in a completely new way. If this goes through the way it can be, it will revolutionize the way we think of keeping cows. And this research project was surrounded with this. Here you see the actual color. It's no fence. The company is already commercially available. And besides this fancy technology, we were responsible to evaluate the paddock and the graze, because now you can put the cows where you want them in the environment. You have the problem, where do you want to put the cows? You need a flexible, robust, non-destructive, cost-effective and timely method to evaluate the sward. There are some methods already around. In the 60s, we implemented a device called rising blade meter. A farmer goes over his farm with a stick, and there's a movable blade, and the higher the grass, the higher this blade will go up. So you can see how much grass is growing on his grassland. We have also, and you are familiar with it, hopefully, hyperspectral and multispectral measurements. I'm not the biggest fan of them in this context because they are not so reliable. I don't know when you fly with your multispectral devices, but it has to be around noon. It has to be on a sunny day, and it takes a long time to process the data. Maybe you're faster, but that makes it difficult in this aspect. In our working group, we've been working since 2010 about a concept called crop surface modeling. We would investigate the field at different plant heights. One in the beginning, you would have the ground level, and then in subsequent times, you would create a model of the surface, and you can very well model the amount of biomass that is currently there by 3D reconstructing the plant height. 2013 we used structure from motion to do this. The disadvantages are high computational demands and the need for multi-temporal measurements. You have to be there at the ground level, and in the grazing paddock, there is no ground level because it's always regrowing. We also investigated terrestrial laser scanning back in 2015. This is where we scanned a mice field with a terrestrial laser scanner, a Regal back then. Heavy equipment, 30 kilos. They are now much lighter, but we have a limited coverage. You all know it from laser scanning. You cannot scan many fields, and it takes long time, and it's in heavy equipment. But with the advancement of technology, we have another solution that we followed in this project, and that was UAV LiDAR. UAV LiDAR is flexible. UAV LiDAR is very fast in terms of availability of the data, much faster than structure from motion. And you have a decent coverage, because with structure from motion you have to cover 5 times the photo amount, and this you only fly once over your AOI. However, it was expensive back then, and it still is, but it's declining. We get cheaper systems, and we think that in the future maybe this could be a solution. Here we have a DJI Imagery 600 Pro, which has back then 16 minutes of flight time, and Regal Minivux 1 UAV with a high precision IMU that is needed for this device. We developed a workflow. We used flight planning UGCS to make custom flight planning. Hello? Ah, yeah. We could estimate the trajectory very precisely with this IMU and another software, and then it's the Regal software that all integrates this. This is basically a standard workflow for mobile LiDAR mapping systems. And then we would use Cloud Compare or LiDAR 360 to analyze the point clouds and do regression analysis. How does this look like? This was one of the point clouds we acquired from one of those paddocks from these grazing areas. And we applied a concept called polygon grid analysis. And those polygon grids are like a grid, but it's fixed in time. So before we had this area of interest, we made a polygon that covers the whole area. And we could analyze only those points that fall into this area. And for this project, we had a long discussions, what is the best size? And we came up with 2.5 meters, because this is in the range of the GPS inaccuracy of the colors, and is a reasonable area to really manage such an area. What happens then? You have one polygon, and you can analyze this polygon and all the points that fall within this one polygon. And you can make a lot of metrics, statistical metrics about the situation with this one paddock. And if you analyze not only one of those polygons, but you keep on analyzing one, and then the next one, and then the next one, and then you have analyzed your whole area. This was our approach to come from the point cloud to the information. There's a little step between, because we need to do some modeling. We have, for each polygon, you have all these observables, like 20, 30, 40 metrics. And then we would use machine learning from those canopy height metrics, combine them with reference data, and do some statistical modeling. And who's interested, I published a paper on this where we did this approach in winter wheat. But here in this case, we used RPM. So I walked with this RPM stick and used this as reference data. That's actually what the farmer is using. And this is what we get out of this. We get a map of all the RPM, compressed sward height, it's called in the end, of the whole area from UAV LiDAR. We compared this with structure from motion modeling. The right side took 5 to 6 surveys to complete this, to get a ground level, and the left one is from one LiDAR flight. So they're comparable, and we think we got further to really have the biomass that is standing here. We can give this information then to the farmer, and what is also directly correlated with this dry biomass, a cow needs a certain amount of biomass, but if it gets too much, then the biomass quality decreases. If there's too much grass growing, maybe you know this from your back door, if there's too much grass, it gets old and it's not very tasty for the cows, so the digestibility decreases. So we can also estimate the digestibility from this, and then you can say, okay, I want a digestibility and a dry matter content of at least so-and-so grams per square meters. And then you get those yellow areas. That would be the perfect grazing areas for your virtual fences. And then we have done our job from the remote sensing, and we would give this information to the collars, and the cows could be steered where they best can graze. So, challenge solved. If I lost you in the methodology part, there's a little low-level explanation of how we estimated this. So we fly over the area, and if we have high biomass area, we get different set coordinates of your LiDAR point cloud, and we use this information to say, okay, here's a lot of biomass, and there's more biomass. We tested this out in a dairy farm from Costello, and they are really people who have the problem that they use rotational grazing, meaning all of their cows go on one paddock. So they have like 70 paddocks, and all of their cows, 700, they go on one paddock. And after this paddock is mowed down by the cows, they go to the next one. And this is how their information system looks like, and this is the information of how much feed there is for the cows. And once this paddock 71 is grazed, it will move here, and then it will regrow until it's time to graze this one again. However, it gets inaccurate over time, and every 1 to 2 weeks, he has to go with a rising blade meter over his whole farm of 3 square kilometers. And this is where our technology could come in, and we applied a test. Can we assess the whole farm? We used 4 flights, each 18 minutes, and it was quite a challenge to perform them within sight. But we managed it. Took us about 5 to 6 hours. In the future, this would be, ideally be performed automatically. And we also collected reference data the day after, and combined these are the LiDAR point clouds you get from this survey. We combined the reference data with the LiDAR point cloud in a polygon grid approach to assess the above ground biomass of this whole farm from UAV LiDAR. And this is the map that would then help not only to manage every paddock, but also to show within variation of the paddocks as an additional surplus. Because now we don't have only point measurements from a RPM device, but we have spatially continuous information about the biomass of this farm. Yeah, we published a paper. We said UAV LiDAR is an effective tool for biomass estimation and enabling more informed grazing management decisions in the end. So I like challenges. If you want more challenges, I found it in free field photovoltaic systems. You might know that there's a big revolution going on in the energy sector. There's a lot of energy production from solar panels that are being installed at a crazy amount worldwide. This is not my type. I'm a big fan of them. It's really nice to have clean energy. But there's more, because there's also the grassland below the photovoltaic systems, below the modules. You can use it for grazing sheep, so there's an agronomical value of this grass below the solar PV modules, and there's an ecological value. It provides ecosystem services such as the biodiversity that is kept by the grassland below the photovoltaic system, below the modules. So we have a research project on the agricultural value of FFPVs. I'm a geographer, but I do not know everything. So I need experts, and I have here expert Dina Hamidi. She's from the Institute of Grassland Science, so she's the grassland expert, and she provides me the insights on the grassland. And I do the remote sensing. So the aim was here to use remote sensing to analyze the effect of the PV modules on the grass vegetation. You can do this if you do rising blade meter measurements again, which you have already heard, or you can also cut the grass, dry it, and analyze it. And you could use normal remote sensing, like satellite remote sensing, but that's not working here because you have the modules in between. So you don't have an unobstructed view on the grass below the panels. So here we came with the idea to use SLAM LiDAR. And SLAM LiDAR is theoretically a good tool to do this because it's very flexible. You can use it handheld, you can use it on a drone, backpack mounted. And here we used the HoverMap ST SLAM LiDAR. And yeah, some advantages that you don't need a real IMU, so it's cheaper compared to a Regal system with a high-grade IMU. And the panels here serve as a kind of a reference structure. SLAM LiDAR is really not working in featureless environments, but here we have a solar park. So theoretically, those solar panels should serve as a good reference. So the question here in this project was, is SLAM LiDAR a tool for biomass mapping also? And we put this on the test. We went to solar parks, which is logistically more challenging than expected. You cannot just go into a solar park. You have to get permission of the owners. You have to get security, whatever. But we managed, and this is the reference measurements we did in one of those parks. I was able to fly a drone. So here we get the Flugfreigabe, Schleswig-Freigabe to perform these measurements. Are we already over the time? I guess so. 2 minutes, okay. I will show you some LiDAR point clouds, not only of the PV models, but also of the vegetation below it. Yeah, here's the reflectance. Maybe one more thing I want to show you is in the end, we did the same modeling as in the other approach. And here we could also already draw some interesting insights on this material. One is that we have a lower heterogeneity in areas that don't have solar panels. And heterogeneity for biodiversity is always a good thing. You want a more diverse environment for biodiversity. And we have an increased heterogeneity under the panels. There's more increase. The plants tend to grow faster, like vergeilen. If you ever grown crops on your at home, they sometimes tend to grow faster because they don't have enough light. They want to reach the light, so they grow faster. And we could show this spatially continuous on a map. And yeah, it's still ongoing, this research. And if you're interested, you can have yeah, questions with me. Yeah, I could end here. If you have more questions or want to have more insights on what we're doing, feel free to contact me. I brought some more stuff. Can I go to the last slide, maybe? Can you do that? Yeah, and then I'm finished. Yeah, thank you for listening. I'll be working in Hippotronic. Contact me starting of January 2026 if you want to have a LiDAR scanner. And thank you for listening today.